So, what is Van de Graaff? Van de Graaff generator is a scientific device used to generate high voltage. It consists of a hollow metal sphere placed above an insulating stand. Inside the sphere, there is a rubber belt running over two pulleys, one at the top and one at the bottom. The belt is made of a non-conductive material such as rubber or nylon. At the base of the generator, there is a motor that drives the belt, causing it to move continuously. Two metal combs, called charge collector, are positioned close to the bottom pulley. These combs are connected to the inside of the sphere and allow charge to be transferred to or from the sphere as the belt moves. As the belt moves upwards, the wrap is changed another comb called the charging comb. The charging comb is connected to a high voltage source, such as Van de Graaff generator or an electrostatic machine. The rubbing action causes electrons to be transferred from the belt to the charging comb, creating a positive charge on the belt and a corresponding negative charge on the charging comb. The positive charge on the belt are carried upward to the sphere, which is initially neutral. As the positive charge accumulates on the sphere, they repel each other due to the same charge, spreading out on the outer surface. This causes a larger electric field to build up between the sphere and the surrounding environment. Because the sphere is a conductor, the excess charges on the outer surface are distributed throughout the sphere and concentrated at its highest point, known as the dome. This accumulation of charge creates a strong electric field around the dome. When a person or object touches the Van de Graaff generator, the excess charge flows through them to the ground, resulting in a sudden discharge known as an electric spark. This spark is a visible manifestation of a high voltage generated by the device.
So, who invented Van de Graaff? The person who invented Van de Graaff is Robert Jamison Van de Graaff. He was born in Tuscaloosa, Alabama, and he studied at University of Alabama. He earned Bachelor of Science of Degree in 1922 and Master of Science of Degree in 1923, both in mechanical engineering. Upon graduation, he worked at Alabama Power Company and stayed there for a year. Apparently, he felt that he wanted more out of life than just working as an engineer. So, in 1924, he enrolled at Sorbonne University in Paris and attended lecture of Madame Curie on radiation. The Madame Curie exposure apparently whetted his appetite for radiation and nuclear experimentation. From that, he received a Bachelor Science degree in Physics in 1926 and a PhD degree in Physics in 1928 at Oxford University. While at Oxford, he became aware of the possibility to disintegrate nuclei through particle acceleration at very high speeds. So, in 1929, he returned to the US and became a National Research Fellow at the Palmer Physics Laboratory at Princeton University. On 1929, Van de Graaff was able to produce the first working model of his electrostatic generator, which produced 80,000 volts. 2 years later, he was able to demonstrate an improved version of his original accelerator, which produced 1 million volts. Shortly thereafter, MIT invited Van de Graaff to join them as a research associate. So, upon that, in 1933, he was able to demonstrate an advanced version of particle accelerator, which produced 7 million volts. During World War II, Van de Graaff was the director of the High Voltage Radiographic Project. The project was focused on the development of precision radiography. Eventually, HVAC became the leading supplier of electrostatic generators that were used in cancer therapy, industrial radiography, and in the study of nuclear extraction. In the 1950s, Van de Graaff invented the insulating core transformer. It generated high voltage direct current using magnetic flux rather than electrostatic charging. Through the use of Van de Graaff particle accelerators, physics researchers were able to accumulate vast quantities of information on nuclear disintegration and reaction, which leads to sophisticated theories of nuclear.
So, when did he introduce his invention to the public? He debuted his invention on 28 November 1933, which made the headlines when it produced a staggering, for the time, 7 million volts. The smaller Van de Graaff generators used for public demonstrations generate between 100,000 and 500,000 volts only. A patent for the Van de Graaff generator was awarded in February 1935. The device won the admiration of none other Nikola Tesla, who wrote a Scientific American article on the new Van de Graaff generator in 1934, declaring, "I believe that when the new types of Van de Graaff generators are developed and sufficiently improved, a great future will be assured to them." Tesla was precise. As always, the generators has been used not just in atomic physics, but also for applications in medicine and industry.
Okay, now I will tell you where the Van de Graaff generator was built. Van de Graaff generator was built by Westinghouse in 1937 at its research facility in Forest Hill, Pennsylvania, and it was constructed for the first nuclear
Van de Graaff generator can make your hair stand due to the static electricity. A small motor makes a roller at the bottom of the machine start turning that roller and causing the belt to turn the second roller at the top of the machine. Although all Van de Graaff generators have these parts, not all of them are made of the same materials and may work a little bit different, but they exploit the relative tendency of materials to lose or to hold on to negatively charged electrons. In the generator, the belts are made of cotton, a relative neutral material. The lower roller is made of Teflon, which is more likely to attract electrons when the lower roller starts moving. It rubs against the belt setting init motion while creating friction between these two parts. The friction causes electrons to jump from the cotton to the roller, which become negatively charged. The belt is left with positive charge. This exchange of charge is called triboelectric effect.
Meanwhile, something else is going on in the metal composition just under the roller. Metal is a great conductor of electricity, meaning electrons move very easily through it because like charges repel each other. The large amount of electrons that have built up in the roller repel electrons away from the tips of the comb. Leaving those comb tips, there's a positive charge. Now, there's an electric field in the air between the positive comb tips and the negative roller. As a result, electrons in the nearby air molecules break away from these molecules and go to the positive comb tips. They leave behind positively charged molecules for ions, which are then attracted to negatively charged roller. The positive air ions cannot reach the roller, however, because the belt is in the way. Instead, they end up coating the outer surface of the belt and are carried up to the top of the machines. The top roller is made of aluminium, which tends to lose electrons as the positively charged belt rubs against it. Electrons move from the aluminium to the belt, giving the roller a positive charge. This positively charged roller attracts electrons to the tips of the comb, creating another electric field that once again strips electrons from the air molecules that are inside it, but this time towards a positive roller. The positive air ions left behind are attracted to the negative comb tips because the top comb is attached to the metal sphere. This positive charge travels towards the sphere and spread out across it. They will accumulate on the sphere until an object, such as this grounded one, comes close enough to discharge it. Then, as long as the two rollers keep rolling, the cycle will begin once again.